So today is the last lecture of this semester. Okay, as I previously said that we are trying to finish this the completeness structure, and then that's it for this semester. Okay, because personally, I think we will finish this class, today's class, a little bit earlier, but would be probably around 2 hours. So in other words, we have probably about an hour. We can finish this an hour early. Okay. So we talk about this set slide. Last time, I think we talk about I think to this slide. Okay. So today we are going to start from here. Okay. So the this chapter really is about setting out some kind of equivalence between what we call difficult problems. Okay. The reason to set up is the equivalence is that we want to combine research effort from different people, okay, in the world. Okay. In the sense that if one problem, okay, has a polynomial time solution, then all the equivalent problems have the polynomial time solution. So in other words, if you want to work on any of these hard problems, be my guest. Basically, your contribution will be as important as you work on these 10,000 difficult problems, because these 10,000 difficult problems have been proved to be equivalent. Okay. But of course, okay, the other way to say it is that, okay, if an exponential lower bound is shown for one problem, okay, remember, these problems are equivalent in the sense of their difficulty level. So if one problem has been shown to have exponential lower bound, all the other problems share a similar nature, okay? So this is why we want to, build this equivalence between difficult problems. Okay. So to sum up, okay, if we can show that the problem pi, okay, is equivalent to 10,000 other, well-known difficult problems, okay, without efficient algorithm, those 10,000 difficult problems are known to have no efficient algorithm. I mean, at least so far. I mean, we don't have like a concrete proof. Any of them, cannot be solved in polynomial time. But at least, nobody can come up with like a polynomial time algorithm for any of them. Okay, any of these 10,000 equal problems. Okay, so if we are able to show a problem pi is equivalent to these 10,000 hard problems, then we get a very strong evidence that this new problem pi is hard. Okay, so what is like the process to do that? Okay, so the following are this three-step process. Okay, the first one is we want to identify the class of problems of interest. Okay. Usually, here we confine our problem to what we call decision problem. Okay. In our word, okay. We want the problem to ask yes or no. Okay. We want the problem to, to expect a yes/no answer. Okay. So, but you may say, oh, but wait a moment. All the other algorithms that we have seen so far are not decision problems. I mean, I will give you some decision problems, examples of them later. But you may argue like, so far like the problem that we discussed like in the other section, in the other chapters, they are not decision problems. But I will also show you, okay, a similar decision problem. I mean, if a problem is not a decision problem, you can come up with a similar decision problem that is supposed to be easier. Okay, and if you can show that supposedly easier decision problem to be hard, then obviously that even if that problem was originally not the decision problem, because that problem is harder than its decision problem variation, then you could argue it is at least more difficult. Yeah, I will show you example later. Okay. The second step is that we want to define the notion of equivalence. This equivalence is built by what we call polynomial time reduction. Okay, even though we say it's a reduction, okay, we are by no means, so we are going to reduce one problem A to problem B. But when we do that, I'm not saying problem A is more difficult than problem B, or problem B is more difficult than problem A. Okay, I mean this word reduction sometimes give you, will make the student misunderstand the whole process. Really, like we are here just to establish the equivalence. Okay, it is not. I mean, yeah, in some sense, you could say, when you reduce problem A to problem B, there's like a easy, difficult relationship, but usually the other way around, we can also do that. So in other words, if you can reduce problem A to problem B, a lot of time you can reduce problem B back to problem A. So having said that, this reduction really does not necessarily means that the problem A is easier or more difficult than problem B, okay? This is just a notion, okay, just a notion. Okay, and then we can prove the equivalence. So first about the decision problem. As I said, the decision problem asks for the answer which is only yes or no. Okay, it doesn't have like a maybe, those type of answer. Okay, so a simple example, okay, is like given an unsorted set S of n numbers and the number key. Okay, we want to know is that key contained in the set S. Okay, so you want to find a particular key in the unsorted set S. Okay, this is obviously a yes/no decision problem, right? Okay. In this case, your input, okay, is S, the set S, and your key that you are searching. Okay, we call that X. Okay, the input X. And there are multiple possible algorithms to solve this problem, obviously. I mean, the simplest one is the linear search. Okay, just look at the elements in set S one by one to see if you can find the key. Okay, so that's a linear search, and the time complexity is a big O n. Okay, it's a linear time. If you want to do it a little bit better, okay, say you are going to search for like a unknown key like many times, it would be a good idea that you sort this set as first, okay, and then you can apply what we call binary search, right? So if the sorting takes n log n, and binary search takes log n, but of course like the log n, is unimportant when we consider like a big O notation, because n log n dominate log n. So the complexity for this approach, sorting and then binary search approach, the complexity is big O n log n. Okay. So the first two make sense. The first case is if you want to do this only maybe one or twice, very few times, then the first approach makes sense. The second approach is that if you want to do this search many times, okay, many times, then you want to sort these numbers first, because you pay a little bit more price once. For the following, search, you can, each of them only take like log n amount of time. So it is like, the second solution also makes sense for certain situation. But the third one works too, but it's a stupid approach. Okay, basically you compute, in the third approach, you compute all possible subsets of S. Okay, and then check each subset, okay, if it contains key. Okay, this one, okay, the first sentence, compute all possible subsets of S. Okay, because you have n elements. All the possible subsets will have 2 to the power of n, this many subset. And then for each subset, okay, if you do a linear search, okay, it is really like the cost is linear. So the cost totally will be n times 2 to the power of n this much time. I mean, this is obviously a stupid approach, okay, a stupid approach. And the complexity is very high, it's exponential, okay. However, in terms of algorithm, okay, it does its job. It's just like it is not a good algorithm, okay. I wouldn't say it's a good algorithm because the time complexity is too high. But on the other hand, well, it answers the question. Okay, it does answer the question. Okay, so here on this page, I just want to show you for a given decision problem, there exists many different possible algorithms. Each may have very different time complexity. Some may make sense, some may be stupid, okay, but it doesn't matter. Okay, it doesn't matter. So, last week we talked about clique, right? Okay, at least we defined clique last week. Okay, clique is a subgraph that is complete. Okay, in other words, for a given graph, okay, a clique of size k contains k nodes, okay, where each node, okay, any pair of this this subset, okay, any pair of this subset has a direct edge between them, okay, in the original graph. That is what we call clique, okay. So in this clique problem, we have input, which is undirected graph, G, which is like VE, and integer k greater or equal to 0. Okay, there are multiple ways to ask this clique problem. The first one we ask is that, does G contain a clique C with the size, okay, with the size greater or equal to k? So this question is a yes/no. Ask for a yes/no answer, right? So the first question is a decision problem. The first question is a decision problem. The second one, okay, again, the same input on the red graph G, VE, okay, but now, okay, we want to output the largest integer k such that G contains a clique C of the size k. Okay, so now it's a different, the second one, okay, it asks for the largest k such that, G contains like, this clique, okay. So obviously the second problem is not a yes/no. It doesn't have yes/no answer. Yes, in particularly for a number, right? An integer, k. Okay. And the third one, okay, on the red graph G, okay, the output is the largest clique C of B. The third one, it's not a decision problem either. It actually asks for that largest clique directly. Okay, so for these three problems, okay, we know the second one and third one are not decision problem. But so this is usually what we call, they are optimization problem. Because we are, we want to optimize something. The second one, we want to find the optimal, largest K. Okay. The third one, we want to find the largest click. Okay. When it comes to optimization problem, usually you are asking to maximize or minimize something. Okay, that's what we call optimization problem. But obviously, you can think about that. Okay, these three problems, although they are different, only the first one is a decision problem. But obviously, the decision problem will be the easiest one among them. Why do I say that? Okay. Obviously, 3 is harder than 2. Why? 2 only asks for the size of the click, size of the largest click, but it does not ask to generate that click. Not generate, like to find that click, as long as you just keep like the size. Okay, so in this sense, 3 is more difficult. If you know 3, you can obviously solve 2, right? Because once you have the click, you just count the number of nodes in this click, and you are able to answer the question number 2. So 3 is harder than 2. Okay, the other way around doesn't work. If you know, like the size K. Okay, the largest click size is K. At least it's not a direct consequence to get that click. Of course, we will discuss how to do that shortly. Okay, and also 2 is harder than 1 as well. Why? Okay, if you are able to find the largest integer K, okay, for the click inside the G, okay, inside the graph, then you just check this K and see that if that makes the first question, the first problem, should you answer yes or no? Okay, because based on the answer of the second problem, you can directly answer the first problem, right? So basically, if you know 2, you know how to answer 1. If you know 2, you know how to answer problem 1. But again, the opposite doesn't work. The opposite doesn't work. Okay, so you can see there is how should I say, kind of like a different level between them. One is easiest. The second is a little bit harder. The third one is the hardest. But nevertheless, okay, you could still, try to use the answer, the solution for the first one to answer, to try to come up with solution for the second one. Okay, here's the way to do it. Okay, if we can answer the first one, okay, then if we can answer the first one in polynomial time, because what we care is the solution is polynomial time or not. Okay, so if we are able to answer the first question, the yes/no decision problem in polynomial time, then do a linear search, something like that. Okay, if we reach a point that we, when we add one more, increase that number, we couldn't find like the answer, change from yes to no, then obviously we are able to answer the second problem. Okay. What is the largest? We want to find the largest size of the click. Okay. We only want to answer the size. Yeah. So doing this is a simple. We just run this the solution for the first one. At the worst case, a number of times, right? Because like it's polynomial, running the polynomial algorithm a number of times is still polynomial, right? So knowing a polynomial solution for problem 1 help you to answer the second optimization problem, okay, in polynomial time. Okay. So then, okay, so you can see that if you have a solution for 1 in polynomial time, you will have a solution for 2 in polynomial time. Okay. How about from 2 to 3? If you have a polynomial time solution for 2, can you have a polynomial time solution for 3? The answer is also yes. How do we do it? The idea is like this. Okay. Given a graph G, say now we will use the solution for problem 2 to come up with like the largest click size K. Okay, say that click size is 10. Okay, so then we arbitrarily remove one node from this graph. Let's say we order this the nodes in this graph from 1 to n. So we remove number 1, and then we run the solution for problem 2 again. If now it tells us that the click size is no longer 10, it will be a number smaller than 10. What does that tell us? It means that, that particular node that we just deleted must be contained in that largest click, right? So we can do this repeatedly, okay, and eventually find that 10 nodes that are contained in the largest click of size 10. Okay, and this one, okay, obviously we are going to run the solution for problem 2 in the worst case a number of times. But if it's polynomial, the solution for number 2 is polynomial, then this solution for problem 3 is also polynomial. So here, okay, I mean like in terms of difficulty, you can easily convert an optimization problem into a decision problem, as I have just shown you. And if you know a solution for a decision problem, okay, you can somehow, and if that problem has a polynomial solution, okay, you can somehow, utilize that solution to answer the original optimization problem. Most of the time, okay, I would say that pretty much all the time, okay, unless the way you transform that original problem into a decision problem, you make some mistakes. Otherwise, it shouldn't be too difficult to do that. Okay. So here, okay, we are talking about the traveling salesman problem. I mean, traveling salesman problem is one of the difficult problems that we talk about like at the beginning of this chapter. Okay, at the beginning of the chapter, we talk about a couple of things, we call difficult problem. Click is one of them. Traveling salesman problem is another one. Okay, so so we could ask, okay, the traveling salesman problem, like given a graph, okay, is there a tool, okay, for the traveling salesman, okay, to visit every city, okay, in other words, every node in the graph exactly once, and that tool, okay, that path is has a length smaller or equal to k. Okay, the previous one, the click, asks for the largest click. Okay, this one we are asked for the smallest one. Okay, so it's a minimization type of optimization, but this version is a decision problem. Okay, it's still a decision problem because the answer is obviously yes or no. Okay, and you can easily come up with like a similar, like optimization problem similar to this one. You have multiple versions, and then you could think about how you can, you can think about the different level between them, and also like if you know the answer for the polynomial solution for decision problem, how do you use that polynomial decision problem solution to construct like construct polynomial solution for the optimization problem for the traveling salesman. Okay. By the way, okay, here we are moving to the next question. Okay, we could, okay, all these problems that we talk about, including traveling salesman problem, including click, okay, the solution can be like we can solve this problem in what we call non-deterministic polynomial time. I know you guys didn't take like theory of computation, so probably you don't have like a good sense what or like a non-deterministic, this term means to you. Okay, the idea is like this. Okay, the non-deterministic means you have unlimited number of parallel processes. Each one can help you to verify something. Okay. I mean, in the current computer science term, you have many, like arbitrary number of threads. Okay? In the older computer science term, you have arbitrary number of processes, okay, and that are run in parallel. Okay? Each one help you to verify. Okay, basically you just generate like all possible answers. Okay, all possible answers, you generate all the possible answers. usually it's easy to generate all possible answers. Okay. But because you have like an unlimited number of like parallel processing capability, right? So you have like each thread or each process to verify if any of them is a valid solution. Okay. And then, you know, whenever like some conclusion is made, okay, if it's yes no question, basically like if any thread give you a yes, you terminate all the threads and answer that. Okay. So by doing so, if one of the threads, like the verification process, is polynomial, then obviously it is like a polynomial for the whole thing, right? So this is called non-deterministic polynomial. Okay. So to answer, to strengthen like what I was just saying. Okay. For example, clique that the problem clique that we just talked about. It is easy to generate all the subsets from a given graph G, right? I know like it's going to be like you know, if you have like a number of nodes, it's going to be 2 to the power of 10. You have many subsets, possible subsets. Okay, but verifying like a given subset of nodes for a clique is very easy, right? You just need to check if, you know, if all these nodes like they are very neighbor to each other. So that's a very easy check. And same thing for traveling salesman. Okay, you can easily, you know, generate an order of the city. For example, if you have 4 cities, A, B, C, D, okay, just generate all the possible city permutations. Okay, for example, 4, 3, 2, 1. And then you check if there's like a link. If there's like a link from 4 to 3, from 3 to 2, from 2 to 1. If there's such a like a path, then yeah, I mean, this obviously makes the traveling salesman true, right? But of course, if not, okay, then yeah, you may need to look for like other path, okay, other path. But anyway, generating possible solutions is relatively easier than verifying. But verifying each answer is also easy. The problem is you may have too many. But this non-deterministic nature, okay, the unlimited number of parallel capability, help you to answer that, help you to deal with that. Okay, so the intuition for this what we call non-deterministic polynomial means that the solution, okay, if you have a solution, the solution can be verified in polynomial time. Okay. The example, if someone give us a tool, we just verify if, in polynomial time, if this tool is of length smaller or equal to k, and also this tool has visited every city exactly once. I mean, this can be done so quick, right? In linear time, pretty much. If a problem can be solved in non-deterministic polynomial time, we call this decision problem is in NP. Okay, this is how we define NP. This NP, okay, the full name is not non-polynomial. Okay, NP doesn't stand for non-polynomial. It stands for non-deterministic polynomial. Okay? So just want you guys to understand that. Okay, let's take a 10 minutes break. When we come back, we will continue our discussion.
的全修就是没有排问题。可是我觉得自贡系的这个东西，它没有排序就引申一个问题，就是它有可能是硬折，就全拿，就是你运气好的全部都拿啊，然后你运气不好什么都没有，对，你水鬼就什么都没有。
对啊，水鬼就是学到都拿去拿。
确实。
第三题有些电脑没有跑，对。
这个就比较好一点。这跑得很好，我觉得手感下面跑道有少，
看手很好，
那也有点烦，有一点烦。
对啊，30分。
有。
对啊。下个再讲说一下。
所以要。
是比较简单的，但是我觉得有点难，而且我不知道怎么使用。
我是直接拿，其实我根本没有需要
demo 吗？
有 demo， 你看这个。要开那个 QE 的课。
应该说这是影片还是要现场拍一段？
哦，就是这个不能在现场，
没有时间，
他就还没开啊。
等下17周跟他说有排事情，他应该不可能排17周咯，期待的这个。
如果排17周，然后到后来才想放，我就是直接录影片，然后跟他说抱歉，因为个人因素人不在台湾。
上次我17周也会在。
我17周
礼拜5跟礼拜2，啊，不对，礼拜2、礼拜2不行。
礼拜2下午的时候也不知道考试几点，
因为只有早上不行啊，考完知道。
回一下也不是说一次啊，那时候很多16周都排好了，对不对？可能，然后他说好，那我17、18周出去，结果他妈有人排到18周，这一步来进行。
对啊。
哦，对。
16周就好了，直接上18周。
对啊，你要留。
你要16周，他有这个东西排17、18周。如果太多人，我刚才应该可能直接取消。
其实我已经录好影片，因为我那时候我不知道。
已经录好影片？
不是，
你连他 demo 什么都不知道，已经录好影片。
我就想说，反正录影片就很简单，那3分钟，然后就是去跑一下课程而已，就没什么。那这个你又不是 QE， 你在这边编译10分钟，啊不编译10分钟，跑10分钟。
还是你用来加入快打6？
你有玩了？
有啊，
我之前玩就玩，后来就
他
电脑跑。
电影的。
那你玩什么？
手搓现代老三。
哦，我是现代老三。
不是，你想一下，你是现代老三对不对？别人就会想说你那个大老板你3个人，但是我又是手搓。对。
我真把 Kenny 玩到很大只，然后电脑跑。
我这台也很痛，我这台我是60 FPS 就已经超痛。
好，我刚300，我刚30。
30超大的。
电脑因为我这几天，我
到现在，原本之前寒假我想玩这个，我也想玩这个。你知道我现在碰到一个离谱的，就是他妈谁给他开，就是
近2个月来第一次看到你们消息。
他们说啥吗？
没有，我没有来啊，我后来没有。
他后来都没来。近2个月来第一次看到你们的消息。
对，我已经多久没有碰到你这个？
会不会有一种可能？
没有，我其实上课回去。
会不会有可能？
应该说，我上一次在这个就是
没关系啊，
他们会剪掉吗？上次就是这样子。
不是我这个原因的，因为我真的觉得，
我听你讲别的。
我的时间要更完好的利用它，就可以做各种作业。那你知道作业系统有写作业的吗？
我知道啊，作业不是吗？
这系统还有？
有啊，作业5啊。
这个东西好像期限
6月17左右。
他怎么还有啊？
对啊。
然后地主不是也有啊？611。
但最后一个作业不强迫写，因为有啊，他
如果系统，
对他是5取4，
所以加分。
所以他做这个。
他成绩不会那么快出来啊。他前几个成绩就2分，他只有2个出来。
普通的啊，我知道普通的。
结果
没有普通的是一般的分站，没有我们班的。对。他也没有啊。
没关系。
我觉得
不可能懂啊，然后我的
分析，
我的那个题目我都是
那就5取4。
不是，然后觉得作业系统它的作业那么多，然后每一个的分数，
他都叫作业系统。
平心而论，其实作业系统一开始就是会有一个作业。
可是
最好是我的意思是它的那个每一个的
成
绩太少，你作业出那么多，你好歹作业成绩拉高一点。
作业总共几趴？
总共有20吗？
然后是什么
15吧。
再少一个才3分呢。
然后一个那个 quiz 跟那个叫什么？出席的那个叫。
那么
说总共5分不是吗？还是一个5分？
出席的。
小考了。
哦，小考。
加分
一个5分也太高了吧？是全部5分，一个5分。
我觉得应该是全部5分那个。
也可能。
对啊，应该没太一个。
假设我拿了一半的分，一半的分。
他不是写名字就一半，还是怎样？
占2分。
没有，写名字25%。
哦。他假设我每次都拿一半分数。
我拿不到一半分数。
我有一次没有。我真的哦。
我每次都有写，但是我每次题目都不会写。
每次都不会写。
好像我这样会只加不到2分而已。那好像没什么差。
算刚好2分好吧？
加2分。
算刚好2分。那差不多就是我专题正常做完的话，应该就是期末要30分。
要不然来，会过就好了。
会过吗？
会过吗？会啊。
应该罚。
作业系统应该就背了，对吧？
对啊，背了。
assignment 28了，assignment 28。
是吧？
然后 midterm 3，final 3，final project
15。final 35。
final project 30。
Dang it！ 然后我现在看到这一整排，我就是一个绝望。
但是final project 占多少
？15。
这样子。
我听到35一下。
他在哪里？现在他在你最大的期中还有那个
期末啦，期中
期中35分，
但是剩下的全部。
关系。
期末
我相信你可以。
那除了作业系统，其他都之前的，因为我那时候在
我光速已经
大一的时候那个 deadline 怎么样？
你有修光速？
我从期末做到
已经过了。
我也听过，
所以你就没有。
除了作业系统以外，
我在小分写作业。
我可以理解这个心情，可以理解。
我有时候吗？
你有课吗？没有课。
在这里。
没错，对。
你看这是什么课？
我忘记。
Okay. So, let's continue, okay. So, here, okay, we can formally define the problem classes P and NP. Okay, we said, okay, of course, this P and NP classes are defined for decision problems only. But as I said earlier, okay, the optimization problem usually has a decision problem variation. So, you know, it is still very, very useful. Okay. So a decision problem, pi is solvable in polynomial time. Okay, I mean the notation is pi belongs to p. If there is a polynomial time algorithm, A such that for any input x, okay, pi x, okay, will be either pi x is yes, if only ax is yes. Okay, so this is if only, in other words, if pi x is no, if x is not an instance of like this problem, then the ax is also no. Okay, so this is not just for the yes instance. This also it also works for the no instance because this is if only if. Okay, so this is about like a polynomial class. Okay, for the non-deterministic polynomial, okay, it's similar. Okay, the same problem pi is solvable in non-deterministic polynomial time, or put it in another word, pi belongs to NP if there is a polynomial time algorithm. Okay, A, but here, okay, a little bit special, I mean, to note, okay, is that, okay, A has two arguments. The previous one, A only has one argument. Here we have two arguments, such that for any input x, pi x equal to yes, if there exists a certificate y of size polynomial x, okay, such that axy equal to yes. So what is this certificate? We will get to that later. So this certificate is something that is a little bit different from the polynomial one. Okay, and also, okay, when I talk about the class P and the class NP, okay, in fact, okay, there's a intersection between them. Okay, there's an intersection between them. To be very accurate, actually, all instances in P can be considered instances in NP. Okay, I will get to that later. Okay. So it will be easier if we can use examples to demonstrate what certificate means. Okay. So for example, okay, back to the click problem, because click is we talked about this many times already. So does there exist a click in G of size k greater or equal to k? This is obviously a decision problem. Okay, is this in NP? Okay, the answer is yes. Okay, because we can find axy. It interprets x. X is your problem, like G and K. Okay, so that's no question about that. So what is your certificate? Certificate Y is a set of C. Okay, set of C. So actually, Y, this certificate is one possible solution. Okay, one possible solution. So, and you just need to check if all vertices in C is a subset of V. Okay, so so it's a subset of vertices. Okay, you need to check if all vertices in C are adjacent to each other, and if C or the size of C greater or equal to K. If that's the case, then C is a subgraph. Okay, it's a clique. It's a clique. Okay, of size greater or equal to K in your graph G, and you will answer this question yes. Otherwise, it's no, right? So this is like satisfy the requirement of the definition of NP. So Y is pretty much a possible solution. So we want this possible solution, the size of this possible solution within the polynomial size of the original problem size. Okay? And we want this algorithm, okay, to be a polynomial time. So that's exactly what we originally mentioned. We want intuition, okay? The intuition is that, a given solution can be verified in polynomial time. So think about this, okay? Once you understand the definition of NP, obviously all the problems in P can be, will be an instance in NP, right? Because, well, the X in P, just use that X in NP, okay? Y, you don't need a Y, okay? Basically, you only have one possible solution, okay? So pretty much like Y can be empty set or something. So pretty much like any problem in P, okay, can be considered an instance in NP directly. So yeah, there's obviously overlap between P and P. The problem is not there's overlap. The problem is that is NP equal to P? That's our question. Okay, as I will get to that later. Okay, so continue. Okay, so is sorting in NP? Okay, unfortunately, sorting is not an NP. Is not in NP because sorting is not a decision problem. Sorting is not a decision problem because obviously you are asking for the elements to be sorted in ascending order or descending order, so it's a computation of the input, right? So it's not asking for like a yes, no. But the sortedness is in NP. So what is sortedness? Okay, checking if input, okay, sequence is sorted or not. Given a sequence of numbers, you check if this sequence of numbers is sorted or not. Okay, this takes, actually takes linear time. Okay, so here, as I said, you ignore Y and check if the input X, which is a sequence of numbers, okay, is sorted or not. Okay, so this takes linear time, and this is exactly what I just said, because this question sortedness obviously is an instance in P, okay, and any instance in P can be explained as an instance in NP, okay, something like that. But of course, the first thing first, it has to be a decision problem, okay? So to sum up, if we show that the problem pi is equivalent to 10,000 other well-studied problems without efficient algorithm, we have this slide already, right? Okay. Anyway, so we finish the first step. Identify the class of problems of interest. So we know like what the definition of a decision problem. We know the definition of NP. So now we are moving to the second step. Okay, we need to define the notion of equivalence, or what we call polynomial time reduction. Okay, so this is our original decision problem. Okay, this is another problem. I mean, they are both decision problems. Okay, so here we want to reduce pi prime, the lower one, into the pi, the top one. Okay, what we are doing is that, okay, we need to find a function f. This function f work on the instances of pi prime. Not work on the instance of pi, okay, work on the instance of pi prime. So you can see f of x prime, and it map the instance of pi prime to the instance of pi, okay, such that, okay, if the original x prime is x, for pi prime is yes, if and only if f of x prime, which is x obviously, in pi is yes. Okay, so you need to establish this correspondence. Okay, so and also this f I forgot to mention, this f needs to be polynomial. Okay, the conversion from the instance of pi prime to the instance of pi, this conversion needs to be done in polynomial time. Okay, let me get the mathematical notation out of the way, and then I will give you some examples. Hopefully, through those examples, it will make you, it will give you a better understanding of this. Okay. So here, okay, this idea, okay. So pi prime is polynomial time reducible to pi, okay, written as pi prime smaller or equal to pi. So honestly, okay, this notation make you feel like pi prime is easier than pi, but as I said, this has no. It doesn't mean there's really like a easy, difficult like relationship between them. But anyway, okay. So if only first there is a polynomial time function f that maps input x prime for pi prime into input x for pi. So this conversion from x prime to x is polynomial. Okay. Second, any x prime, if pi prime x prime, okay, is yes, then pi f prime, pi of f of prime, pi of f of x prime, okay, sorry, okay, will be yes too. The other way, pi prime x prime is no, then the other way, the other one is also no. Okay, so I prefer the lower definition. Pi prime x prime equal to yes if and only pi of f some facts are very important, but at this moment it may be confusing to you. Okay, so if pi is in P, then pi prime will, and the pi prime is reducible, polynomial time reducible to pi, then pi prime will be in P too. Okay, another fact is if pi is in NP and the pi prime is polynomial time reducible to pi, then pi prime is in NP too. Okay, so these two facts, we will come back to this slide later after we finish some examples. Then it will be very, very obvious. Okay, the third one, the transitivity. This one doesn't need any example. Basically, you just follow the notion. Obviously, if pi double prime is polynomial time reducible to pi prime, and the pi prime is polynomial time reducible to pi, then pi double prime is polynomial time reducible to pi. This transitive property obviously hold for the for this polynomial time reducible notion. Okay, because you can write this once for pi prime pi. You can write this again for pi double prime and the pi prime, and then you have one function f, and you have another function f prime to convert instance of pi double prime to pi prime. Then you just from that pi double prime instance, you just do the polynomial time conversion twice to convert to instance in pi, and all the argument should hold still. So this is obviously the transitivity property holds. But the fact one, fact two, is not that obvious. But with some example, it will be easier for you to understand. So let's talk about click again. So click the input on the directed graph. Okay, G, B, okay, and an integer k greater or equal to 0. We want to output, is there a click C, okay, the subset C of B such that every pair of vertices in C has an edge between them, okay, such that the C size is greater than K. Okay, this one, okay, is a decision problem because we want to ask, is there this click C? We are not asking the output to show us that C. We just ask is it true or not? Okay, so it's yes or no question. So for example, the graph on the right hand side, it has a click of size 3, right? It's I hope this is obvious to you. Okay, the top 3 nodes form a click of size 3. So now you understand click, right? Let's talk about the independent set. Independent set is another difficult problem in graph theory. The definition is slightly different. It's for undirected graph G, okay, and again we are given a number K. All we want to output is there a subset S? We want to find the subset S of V, okay, such that this subset size is greater or equal to K, such that no pair of vertices in this subset, okay, has an edge between them. So this is almost exactly the opposite of click. In click, we are asking a subgraph such that any pair of nodes in this subset has an edge. Okay? The independent set is that we want to ask a subset of nodes such that any pair of them have no edge in between. Okay, so for example, okay, you can see that, okay, this graph, okay, the two vertices that we circle obviously is an independent set, right? Because, well, they have no edge between them, right? You may argue, can you have a bigger independent set? Can you have a bigger independent set? The answer is sadly no. Okay, if you try to have a third node, okay, in this independent set, you will find that, you just couldn't do it. Because if you include these two nodes, obviously you have to exclude their neighbors, right? Once their neighbors are gone, there's no other nodes in the graph, right? And you may argue, how about if we start with some other nodes first? Okay, so for example, you can start from any node. Okay, say you start from this node, then you have to exclude these two nodes because they are neighbors of this node. So once you exclude these two nodes, you only have these two nodes left. So you can only pick one of them, right? So some simple, observation will tell you that the maximal independent set in this graph is 2. The size is 2. Of course, you may have different set, but the maximal independent set, is 2. Okay, this MIS, MIS is known to be a difficult problem because we want to do this for any graph. Of course, its decision variant is like this. Okay, given a graph C and the number K, is there a subset of nodes? Okay, such that with size K, greater or equal to K, okay, that this subset is a maximum is an independent set. So clique, you know the definition of clique, right? An independent set. Now, hopefully, you know the definition of independent set. Hopefully, okay. So how do we do this reduction? Here's the thing. Here we are doing polynomial reduction from clique to independent set. Okay, so because we are doing the reduction from clique to independent set, so clique is pi prime, and independent set is pi, right? So, okay, this one, the input G equal to BE, okay, K. So we are using G equal to BE, K, okay. This one has X, okay. True. This is clique, and then construct the input C equal to V prime, G prime equal to V prime, E prime, K prime to independent set. Okay, we are constructing input, this one. such that G has a clique of size greater or equal to K if and only if G prime has an independent set of size greater or equal to K prime. Okay. So the idea is just we said, okay, K prime equal to K, B prime equal to B, E prime equal to E. So they are exactly the same. And then this reduction is done. The reason is that C is a clique in G if and only if it is an independent set in G prime. Okay, complement in G's complement. So there's something wrong here. Okay, it's like this. Okay. So let's give a graph. Okay. We say G has a clique of size K. G has a clique of size K. So this is a clique. Okay, it's a clique of size K. Okay. Let's construct G prime from G. This is G prime. Here, it's a slightly special. Okay. The G prime, okay, the vertices are exactly the same. Vertices are exactly the same. Okay. So this one is a VE, right? So this G, the edge, the vertex is also the same. But the edge is the complement of E. Here is E bar. What E bar means is that, okay, if the original graph, okay, if these two nodes have an edge, then we don't have an edge. Okay? If these two nodes do not have edge between them, then we have an edge. Okay? So it's complement. Okay? So this is like a VE, it's a VE bar. Okay? And then you consider exactly the same vertex. Well, let me just use C, but probably that's for C prime. Okay. So the way we construct G prime, okay, if originally we have an edge, we don't have an edge there, right? If originally we do not have an edge, then we have an edge. So think about that. If this is the case, say originally this C is a clique of size K. Now this C prime obviously is a size K, right? Because we know the vertices do not get changed, right? So this C prime also has K nodes. But because they each pair in the original graph they have edges. So after the conversion, all these nodes in C prime, they do not have edge between any pair of them, right? So this one becomes the independent set. If this one is click, okay, if this was click, then the converted one is independent set. Okay. So this E, oh yeah, I made a mistake. This is E bar. It is true, but I didn't notice this bar there. Okay, but anyway, you get an idea. Yeah, I thought like, how come they are the same? Okay. So what does that mean? What is the consequence? I mean, first, this is a polynomial time reduction, right? Because you only need to check like, this construction takes how much time? How much time does it take? It takes like a number of edges. This complexity. Okay, number of edges. Like you go through every pair. Okay, or in the worst case, it takes this much time because you check every edge, right? You check every edge, every pair. If there's an edge, you change, you get rid of that edge. If there's no edge, you add an edge. So you check every pair of the vertex. Okay, so the time complexity is like that. Okay, so it's a polynomial time reduction. So what does that? What is good for this polynomial time reduction? Think about this. Now, okay, now let's say we are able to reduce. We are able to reduce clique to independent set. If the independent set has a polynomial time solution, if the independent set has a polynomial time solution, then okay, how do we solve the clique? Okay, we just need to convert our instance in clique, okay, into the independent set, okay, and then throw this instance into the solution of the independent set, okay, and it will answer yes or no, right? And that yes or no can be directly used to answer the clique according to this polynomial time reduction definition, right? And the whole process, the conversion takes polynomial time, and then you call the solution of the independent set, that's polynomial time as well. So the polynomial time plus another polynomial time is still polynomial time. So that means what? That means if there is a solution for independent set, there will be a solution. If there's a polynomial time solution for independent set, there will be a polynomial time solution for clique, right? once we are able to establish this hormonal time reduction from click to independent set, okay, then if the independent set has a polynomial time solution, then click has a polynomial time solution. Okay? And the inverse, okay, if A implies B, obviously not B implies not A, right? Okay? Let me write it down. Let me write it down. We just say, if independent set, okay, is P implies click is in P, right? Let's just talk about that, right? So under the you know assume. Well, it's not assumed. We already proved that because click is polynomial time reducible to the independent set. So if independent set is in P, then click is in P. Okay. So the other way around, if click, okay, not in P. What do we mean by not in P? It means if click cannot be solved in polynomial time, if click cannot be solved in polynomial time, then IS. Right? Right? This is a very simple logic, right? Very simple logic. P, A implies B, okay, not B implies not A, right? So, that is really what we are talking about here. If we are able to reduce like, you know, pi prime to pi, then if pi is in P, then pi prime is in P, okay? And if pi is non-polynomial, non-deterministic polynomial, okay, then pi prime is non-deterministic polynomial. I mean, non-deterministic polynomial, I mean, here I should make it like, to make it more concrete. If this is not P, then this is not P. Okay. Actually, most of the time, what we want is the second fact. Is this one. This one. Okay. So let's recap. So we define a large class of interesting problem. We call them non-deterministic polynomial. Okay. So we have a way of saying that one problem is not harder than another problem. Okay. I mean, be very careful. I say not harder. I'm not saying it is more difficult. Usually, when we do a reduction, they are equally difficult. They are equally difficult. But you know, this notion, I mean, I just hope you don't get confused with this notion. So our goal is to show equivalence between hard problems. So we have like many, you know, difficult problems. Okay. Actually, there's a book with black cover, like it was a long time ago, like when I was like studying like for my master's degree in Indiana University. That was like 1993, 94. Yeah, because my major at that time was like a complete like a complexity, you know. So so I was like that book was kind of very famous. Okay, that book alone lists like I think like thousands, at least like a couple thousands like NP complicated problems. Okay, so it's like yeah, I mean I don't, but that book, because I moved like because of moving from one place to another, that book is I can no longer find that book. But that book is a famous. If you want to study that book is must read. Okay. So anyway, so we show the equivalence between difficult problems, and be very careful about this a lot of time. This reduction can be done either way. So that's why you see that these difficult problems, actually they are equally difficult. Okay. So we can reduce, we can show reduction between all pair of problems. Okay. And but we don't need to do that for every pair because of this reduction. As I said previously, it has a transitivity property. So you only need to show like, okay, it can be reduced to one problem, and then, one problem can be reduced to that, and then, usually it's good for all the other direction. Okay. So instead of showing that all problems in NP are reducible to a fixed problem, okay, pi, we actually show some problem, pi prime NP is equivalent to all difficult problems. Okay, and then we only show one of such problem. Okay, can be reduced, polynomial time reduced to pi prime. Okay, that's good enough. Because of the transitivity property. Okay, so let's, it is slower than I anticipated originally. But anyway, let's take a short break and we'll come back. We'll finish this chapter. How many slides? We have like about 10 slides.
去考啊，姑且得个60的那个，没有。
不用去考啊。
要不要助教？
啊，
助教，
被我吃，看你要怎么吗？
没有，我问助教问题。有文件。
4个除以，
然后那你跑得很快啊。
还行。但是我把规逼跑半小时。
你说第5个啊？
就是打那个T打，对吧？我跑了半小时以上。
跑了半小时，
我在讲。
跑了2个小时。
2个小时。
因为我只给他2个CPU。
哎呀，一定要给他开到6才对。
你也在跑很久。
对。
没事，我跑一次也要半小时。我再给他开多个core，然后就出现莫名其妙的。
我要怎么联网？
他们自己会连不是吗？
他会重新出机的联
是吗？
他没有。
上面这边，这里来这里，wire。
哦，
我还在想说，我
你把它关掉，然后你说没有玩过。
我不是关掉，他跟我说没有玩就没有玩。
没有啊，但是我第一次他没有啊。
一开始
你要把它那个进去。
我懂你说。
你要不要有一个选项是可以开在里面接一个公用资料夹件，所以把这个接一个公用资料夹件给大家问题。看对好吗？
他的问题是
那个你 V box 先开一个 share file。
真丢云端的。
然后是还可以装到我的范围。我这边直接修不了。
这我后来设定一下，想说
对。
好不容易，他就说2个必修还可以上到。
他们说
我们就云端。我喝云端。
有次做一些我很少教。
计算机。
对啊，我后来就直接可能自己做就把它改出来。可以，当然可以。
不行吧？
哦，我有开那个双向。
我有开手，我有开手。
我是开双向把它赶出来的。
说
我的话，
不是我先问助教那个问题啊。
你要问什么问题啊？
我要问他选择题要不要写过程啊？
哦。
他如果每个学校都要写过程的话，他比那个叫什么？
应该是就直接对吧？
我也是觉得应该不要，但是我把那几个问一下，不然选择题要写过程是这样。
现在里面应该有个正确的，对，好，是的。对，好，你把东西丢到这里面，你把东西丢到这里面就变成正确的。你是
因为那个 AI 叫我要关法，
问这两个。
先有的，因为我先就是把这个那个本地文字档代表那个没有，先教，我怕我刚说错，然后看还行，
然后 V 咯。所以明天的 demo 都要
我就下课跑开你就直接拖着，干嘛？人家就是那个不能把那个就是拖他人家录制这样子，这个不是讲你只把拖进去就好，就是把拖往里面就
坐在这里的。
我就坐在旁边。你现在讲之后会发挥的。对，我跟他。
我只开过最新版，我之前从来没有点开过。
你们最近有用的我忘记是。
屁啊！关着了。你看，他红的。
我靠，我们都不是说是有关系要去开个 WS，看一下。
说这一次改那个结束这一切。
哎，干他没关呢。
因为我的使用者名称是中文，那你直接在系统底下直接中文。
我也讲清楚一点。
这边
地毯呗。
一个你的看的传说。
那你后来觉得？ 我
这没有是很理解，那个就是有可能出去的，也有可能不出去。
哦，可是这样那有点是产品在的，因为我们现在是有一点写到感，就是我们上次我像我个人3个小时基本上我实体是没有写到，就是我最后一题是没有写到。3小时啊，或者考3小时前。对啊，
怕时间来不及。
对啊，直接会来不及。
你们觉得选择题会有帮助吗？
会。
会。你们觉得会有这个？
对啊。
好啦，那我就还是跟以前一样，有一些出选择题，有一些就是我就维持题目形态，好不好？对，因为那想一下。所以像变成选择题，那时候是那个我去年是出几题选择题。
去年
就是我会贴上去的 sample final。
可以现场看。
先上课啊，我们这样课上不吵，至少课要上完，要不然的话不然你们就先2个小时可以把这上完。OK。So the first problem, okay, the first problem, is a famous one, okay? It's called the Cook's theorem, okay? A guy named Cook, okay, he proved that, okay, the SAT problem, okay, the SAT problem, any NP problem can be polynomial time reduced to satisfiability problem. Okay, so in other words, this red line has already been established. All the red line, not just one, all the red line. This pi, okay, is the first problem for NP complete problem. Okay, the first problem. So, if you want to introduce a new problem into this class, the only thing you need to do is to show any instance in NP complete, like a class, can be reduced to your problem. Then your problem is NP complete. Okay? I mean, of course, the first thing first, you need to show your problem is NP. Once you show your problem is NP, this red arrow is automatically provided. Okay? So that Cook's theorem basically states that, okay, first we need to know what is SAT. Okay, what is SAT? SAT is like this, okay? Given a formula, okay, 5 with n clauses over n variables. Okay, we want to check if there exists true false assignment to these variables such that the whole formula satisfies. Okay, in other words, the whole formula, the evaluation becomes true. Okay, 就是那个你在离散数学里面学到的那个，就是那个什么 什么 P and Q 什么 or R 什么那个什么，你可以再加一些 not 啊什么东西，然后刮胡随便你弄 ，OK， 然后这样子 ，OK，like a form compound proposition like that. Okay, of course, like it is like formed by a lot of variables, right? So say we have n variables, and we have n clauses. Okay, then actually the clauses doesn't matter. But the more important thing is, we bound the n variables, and then for those variables we can change their name to be x1, x2, blah blah to xn, right? So it would all look like something like that. So when we check if there exists a true-false assignment to this variable, such that we can make all this the whole formula satisfy. We can satisfy the whole formula. It makes the whole formula to become true. So so this is called SAT. Okay. The unrestricted SAT, okay, Cook theorem basically shows that, okay, so he proved in like 1971, so it's more than 50 years ago, okay. So first SAT obviously is an NP problem, right? Because it's true false. It's yes no. It's yes no. Whether or not there's an assignment to satisfy the whole formula, and obviously it's just like involved like assigning like a true false to all these variables. So it's obviously NP, and then okay, Cook in 1971, he showed that any problem instances in NP, okay, that problem can be polynomial time reducible to SAT. So this is profound. This is profound. This is important. Okay, why? Because this allows us to establish all those red arrows. Okay, you don't need like to do this one by one. Okay, basically like as long as you show the problem is NP, look, it's relatively easy to show the problem is NP. You only need to show it's a decision problem, and the verification of a solution is take polynomial time. That's it. Okay, that's pretty much about it. Enough to show the problem is NP. And once it satisfies NP requirement, okay, the Cook theorem basically shows that, okay, that problem can be polynomial time reducible to SAT. So the first one is SAT. Okay, and then okay. Honestly speaking, okay, there's a few things I want to also mention about this here. Okay, so you may wonder like, why do we need to talk about N clauses? What is N clauses stand for? Okay, there's like a variation called 3SAT. So we can easily show that 3SAT, SAT is reducible to 3SAT2. Okay, so that like what is 3SAT? 3SAT basically stands for like this. Okay, 你知道那个CNF conjunctive normal form， 就是任何那个 logical clauses 可以被写成 any 我就快速讲一下 ，OK， I just quickly talk about that. Okay. Any logical clauses, okay, can be converted into can be converted into something like this. So inside each parenthesis, we have like, for example, P1 or P2 or da da da, or P5 or P10. Okay, blah 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 blah. So inside the parenthesis is like some variable, and of course you can also have not. You can also have not. Okay, but anyway, inside the parenthesis, like it only contains some not and some or. Okay, in between like each variable. Okay, and the outside is and. So it's and. Okay. We know like generally all the SAT, any logical proposition can be converted to something like that. Okay, and also like let's say if you have like a P1 or P2 or P3 or P4. Okay. You can do something to break it into introduce a new variable. Say this is a this parenthesis has 4 variables there, right? You introduce a new variable, something like this. Okay. Then I mean this one can be shown to be equivalent to this one. Okay, so you can break like a long clauses into each parenthesis contain only three such variables by introducing some new additional variables. Okay, and we can show that this additional variable, the introduction of additional variable, number of these additional variables is bounded, okay, by by polynomial. Okay. So this is like so eventually all these like unrestricted stuff become like becomes like this something and something and something and something. So each parenthesis contain, at the most three stuff, P3 or P10 or not, all of space, P10, and then P2 or not, P11 or P5, okay, something like this. da, 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 da. So each of these parentheses contain at the most 3. Okay, so this type of variation of SAT is called 3SAT. SAT. So as I said, so as previous I just showed, I mean, of course, like quickly, like SAT can be reduced polynomial to 3SAT. Okay. So for example, because each of these is less than 3, right? So you have 3 here, you have 2 here. Okay. So basically, like, so this is like a 3SAT. Okay. So basically, what it really means is like because obviously 3SAT is also NP, so we establish SAT and 3SAT, and all the NP point to here. P1, P2, blah, 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 blah. So obviously, if once they point to SAT, they also point to 3SAT, right? So all those red arrows guarantee that. So if you have a new instance, so a problem pi such that for any pi prime, okay, is in NP, we have pi prime, okay, that is polynomial type reducible to pi. This pi is SAT. It's called. If you have like a problem like this with this nature, we call the problem pi is NP half. So obviously, the first problem with this nature is SAT, and then I just showed you 3SAT is also NP half. And an NP half problem that belongs to NP is called NP complete. So SAT, 3SAT, they are both NP complete. Okay? So we finally are able to define NP half, NP complete. And then, so we need to, the first one is like, Steve Cook. Okay, this guy is Steve Cook. So, so he proved that SAT, so all NP problems can be polynomial time reducible to SAT. So all this red line has been shown. Okay, and from click to independent set, we already know how to do that. So we only need here, okay, this graph, okay, we only need to show how to reduce SAT to click, how to reduce independent set to vertex count, and we're pretty much done with this chapter. Okay, so all the above problems are being complete. I mean, obviously there are a lot of incomplete problems. I mean, but we couldn't talk about all of them. I mean, we can only select a few. Okay, so we still have like about less than 30 minutes. So that's first. We need to show, okay, how you reduce SAT to click. Okay. So click, I mean, I think I don't want to talk about this again. So how do we polynomial time reducible SAT to click? So given an SAT problem with a formula like this, So C1, C2, blah, 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 to Cn, they are, each Ci represents a class with, some variable. Actually, we could, as I said, because we already showed 3 SAT, is incomplete. So we can combine each Ci, its variable is less than 3, less or equal to 3. Okay, so we need to show, we will produce a graph, okay, VE and the K such that, okay, the SAT, okay, this formula is satisfiable if only the produced graph, okay, has the clique of size K. Okay, if only. So how to do that? The idea is like this. For each neutral, okay, key occurring in phi, we create vertex VT. Okay, so we create an edge VT to VT prime. Okay, under two conditions. Okay, if only these two conditions satisfied. Okay, first, T and T prime are not the same class. Not in the same class. If they are in the same class, we do not, let me repeat, we do not introduce an edge. Okay? And the second, okay, T and T prime are not negation of each other. Okay? Maybe it will be easier if we use an example, right? So let's use an example. For example, here we have like these three clauses. Okay, x1 or x2 or x3, parenthesis and not x2 or not x3, parenthesis and not x1 or x2. Okay, so here, okay, we have x1, x2, x3, x2 negation, x3 negation, and x1 negation, x2. Okay, so you can see, so this is like this represents the first class, x1, x2, x3, and x2 negation, x3 negation. This one represents the second class. Okay, and then the third class, not x1 and x2, here represent the third class. And you can see that in between the variable, okay, in the same class, there's no edge between them. Okay, so there's no edge between these two. There's no edge between these two. And also, we have an edge between like elements of different class, as long as they are not negation to each other. So for example, okay, x1 negation and x1 does not have an edge. Okay? So far so good, right? This construction of graph takes only polynomial time, right? This graph, okay, construction takes only polynomial time, right? Because you just scan through like the variables and try to create like this edge. I mean, obviously it doesn't require like exponential time to do the job, right? Okay, so now we claim this graph has clique 3 if and only if the original problem has an assignment that satisfies make the whole thing true. Okay. n clauses, so it's greater or equal to n. Actually, it's like in this particular example, n is 3. Okay. So how to show that? So first, because it's an if only, so we need to do it both ways, right? So for example, okay, if you want to have if you already have an assignment that satisfies this the whole thing, the whole like logical proposition. Okay, for example, these 3. Think about this. Okay. According to our assignment, first, these 3, okay, x1 equal to false, x2 equal to true, x3 equal to false. Because each clause is like contains a lot of or, right? So one of them must be true, right? One of them must be true. 就我们这边每一个刮弧里面是3个这个最多3个这个 literal 的这个 or。那这3个 literal 3个或3个以内的 literal 里面至少会有一个是 true， 对不对？对不对？要不然因为你要整个 literal 是 true， 要不然的话，因为literal 应该说 clause and clause， 只要任何一个 clause 是 false， 你整个就会变 false。所以说呢，你每一个 clause 都要是 true， 那每一个 clause 要 true 的结果就是每一个 clause 里面的那些所有的 or 至少有一个是对，一个是 true， 对不对？好，那你现在想想看，那你如果找到像这样子，你让这个 set C OK contain one satisfied literal OK per clause OK there must be such a assignment, otherwise as I said like the whole position wouldn't be true OK so those literal because they belong to different clauses. Okay, so there is no edge between them, and they must not be, opposite to each other. Otherwise, you wouldn't be able to assign like a right value to it, right? So, this one must be a clique according to our graph construction. So if there's one way to satisfy the whole position, okay, then you can find like one variable, one literal from each clause, and those like literal from one literal from each clause. Okay, so I mean you must form this vertices must form a clique. The other way around. Okay, the way we construct this graph, okay, because within one clause there is no edge between them, right? So if you have like a k, if you have like an m, if you have an m clique, like each vertex, okay, in this n clique must come from different clauses, right? Otherwise, if any two of them belong to the same clause, they do not have edge between them, right? The way we construct it, we do not assign edge between like literal inside two literal inside one clause. So this like if we have a clique of the size n, those literal each of them must come from different clauses. And then, you know, and then the way we assign is like, you know, this, you know, because they have, this is click, right? So this age, okay, indicate that they are not contradicting to each other, because like the second assignment, like we guarantee like if there's an age, then this T and T prime, okay, they are not negation to each other. So in our work, we are able to assign, give assignment of P and T prime to make both of them true on the two ends. So having said that, okay, you know, if you have a click, that click, okay, at the end, you know, will create, you know, assignment of literal to make the whole proposition true. Okay? So we are able to, you know, do it both ways. Okay? Then we have this like, we are able to reduce SAT to click. Okay? We reduce SAT to click. So, yeah. So we finish that part. Okay? So we construct reduction that maps yes input to SAT to yes input to click. No input to SAT to no input to click. This reduction works in polynomial time. Okay? Construction of graph, as I said, it's polynomial time. So SAT is polynomial time useful to click. So click is empty half. And also we know click is in empty already. So click is empty complete. Okay? So the last one. Vertex count. This is a new version, right? So this new version, but this new version is not, it's really not any more difficult. Okay? It's also a graph version, a graph theory version. Given undirected graph, okay, vertex count, okay, and also a k value, okay. We want to answer, okay, true or false, or yes or no. Is there a subset C, okay, the subset of vertices, okay, such that each edge in this graph is incident to at least one vertex in this set. So for example, look at this example. These two vertices, if you select these two vertices, okay, then all the edges, okay, are either have two ends in this subset, or any edge have at least one end in this subset, right? So that's called, this subset is called vertex cover. I mean, the cover stands for it cover all the edges. Okay, cover all the edges. I mean, in the old time when computer networks was still very popular, you know, the vertex cover was like a very important problem. Okay, because like you know, in computer network, obviously, if you are able to have a theorem that guarantee, I mean, cover certain stuff. For example, if you are able to cover every edge, that means in computer network, it covers every, you know, connection, right? So this is also something that is important in computer network. Okay, so this was like popular and important, but now because not too many students are interested in computer networks. So computer network, it's not like it's not important. It's it has become like something like very basic. You know, everybody uses computer network. I mean, you have your cell phone like with you all the time, but you just very few students still do that. Very few people still do that network research. Okay. By the way, okay. vertex column. Okay, so now, okay, remember our graph. So here we want to reduce independent set to vertex column. Okay, how do we do it? I mean, I probably need to mention one thing. It's like, obviously you could reduce click directly to vertex column. You don't have to reduce click to the independent set, and then from the independent set to reduce the vertex column. I mean, you could directly reduce click to vertex column. I mean, there are many different ways of reduction you can do. Okay, it's just like here we couldn't show all the possible reduction. That each one takes some time. Okay, so we just pick some examples. Okay, to show you. Okay, but also we want to maintain like diversity. So here we just pick this view. So vertex counter. So we want to show independent set vertex counter. So I hope by now you still remember what we talked about, like what is the definition of independent set. Okay, so in independent set, okay, okay, so given an input, okay, which is like the graph and the k in independent set, we need to construct an input, okay, C prime, okay, K prime to vertex column such that, okay, the G has an independent set of size greater or equal to K if only G prime has vertex column of size smaller or equal to K prime. Oh, by the way, I forgot to mention the vertex column, okay, I mean, in a clique and independent set, we want to maximize the size, usually we want to maximize the size. But in vertex column, we want to minimize the size. Okay, so the optimization like direction is slightly different. Okay, so here it is actually easier than you may think. The construction is like this. Okay, your V prime is just V. Your E prime, your age, is just original age. Okay, so the graph remains identical. The only thing that need to change is your K. Okay, or the K in the independent set. Okay, then the K prime in the vertex column becomes like the size of V, which is n. Remember, no, n minus K. Okay, so we say such a graph, well, actually it's the same graph. The graph, okay, has an independent set of size K, okay, if only, okay, the same graph has a vertex cover of size n minus K. Is it true? Okay, actually, okay, if we have a set S to be an independent set in G, then V minus set S will be a vertex cover in G. That is why this is K, S, the size of S is K, and the size of V minus S is n minus K. Okay, so think about this. Okay, let's use like this one. That's an example. Okay, the independent set. I mean, previously we discussed about this exactly the same example. We said the red circle are independent set, right? And it is the maximum one. Okay, I just told you like we couldn't find like any independent set greater than 2, right? Let's look at the complement. These three nodes. obviously form a vertex carbon. All the edges, okay, has at least one end in this subset, right? These blue circles. Why? Think about this. If vertex carbon and this independent set, if they are not complement to each other, if there's a one set, if there's a one node that is not independent set, okay, not independent set, and it's not like vertex carbon, say we have another node here. That node will be able to be included in the independent set, right? Okay, if you have another node here, that node will be able to be included in the independent set. Okay. So basically, these two things, vertex carbon and independent set, they are complement to each other. Okay, although they have very different dimension. Okay, and because of that, this reduction is done. Okay, it's done. So we are done with this chapter. Okay, so that's it. Well, it takes much more time than I originally anticipated. Yeah, but we still have 3 minutes. So to come back to the final exam, like how many 你有多少个这个选择题？其中，这是你们觉得选择题有帮助？好了，反正我就按照这样子的样子出，选择题我可能会出5题，好不好？选择题出5题，然后剩下出最大题，好不好 ？OK。然后有一张曲序不要忘了，然后不带这件事情 ，OK。好，那有没有同学有任何问题 ？Any question? Because today is the last lecture.
期末考范围是什么？全部。
哦，就全部，但是期中考之前的占3成。OK， 期中考之前占3成，期末考占期末考以后的占7成，然后会有你们那个到时候出去把那个。就是现在剩下学生就是退掉，有一些学生退掉，剩下的学生的那个期末考的那个平均给我。
好。
对，好不好？我会按照那个去调整我的那个 bonus。OK， 譬如说，如果期中平均假设是50分，那我假设我平均要70分吧，我会多给30分的 bonus， 就让你们去赚，好不好 ？OK。
这样一个现成的差异，因为如果考太烂，他们现在已经走掉了，他们已经走掉了，然后可是那张考卷本身的难度就放在那里。
那我一定要背上现在的那个平均来做决定啊。对，
我们是现在。
对啊，我那时候跟你们讲说，你要劝人家不要退啊。对啊，因为我那时候就讲嘛，我那时候在那个期中考那个考卷那个改出来的时候，我就跟你们讲过，我说我会背上期中考的那个情形，然后再做动态调整。但是会被因为有同学退掉，所以会看一下最后的数据。
85个点，对，对，然后换折中点80，就是多从70到80而已，应该多
看一下，我现在我先看一下。